Okay. Now, a heat pump is simply the reverse of this. What a heat pump does, work is done on the heat pump and it supplies energy back to a hot reservoir. Okay, and takes away energy from a cold reservoir. Okay, so naturally heat will not travel from a cold body to a hot body. So a heat pump makes that possible by means of an external external work done. So again, we have an ideal heat pump where the delta U is 0, and therefore the work done will be equal to the heat supplied to the hot reservoir minus the heat taken from the cold reservoir. Okay, so this relationship stays the same for both of them. After that, there is a description. It's a little descriptive for the refrigerator over here and how a refrigerator is an example of a heat pump. So you want to go into details, or rather at least descriptive nature of the how a refrigerator works. And also you can probably give some examples of what are some examples of heat pumps, for example air conditioners, or you have a condenser and an evaporator, etc. How you can reverse it in figure 1.015 in page 10. So you want to go into a little bit, not too much in detail, because it's not usually the description that is tested for these parts. But yeah, one of the parts of the question might be describe how a refrigerator works. So they must know what are the different components of a refrigerator. Okay, now I think the last part of 10.2 is about a Carnot engine. So a Carnot engine. So any engine, for example this one, is operating between two reservoirs. A hot reservoir and a cold reservoir. Let's say the hot reservoir is at TH and the cold reservoir at TC. So if we draw the pressure volume graph, okay, this engine will obviously have a few strokes in which it completes each cycle, and then it repeats that cycle in order to get to convert heat to mechanical work. Now let's say this is TH and this is TL. Now for any two reservoirs operating between a hot temperature and a cold temperature, you will always have an ideal theoretical engine called a Carnot engine. Okay, this is named after the scientist who discovered or rather theorized this. This engine has the maximum possible efficiency in between these two temperatures. Now, the steps or the processes involved in a Carnot engine are a first step of an isothermal expansion, then an adiabatic expansion, followed by an isothermal compression, followed by an adiabatic compression. Okay, my graph is a little skewed here. I can extend this. Okay, so these four steps operating between these two temperatures is the ideal engine, and it has the highest possible efficiency. Okay, and the efficiency is given by 1 minus temperature of the lower or the cold reservoir divided by temperature of the hot reservoir. This is called the Carnot efficiency and is the maximum possible efficiency for any engine operating between these two reservoirs. From here we can see that the only way in which an engine can attain 100% efficiency is if the cold reservoir is at 0 Kelvin. These temperatures are in Kelvin. And because we know that we cannot build a Carnot engine as it is a theoretical engine, we also know because of that fact that we cannot attain a temperature of 0 Kelvin. This is explained very well on page 12 with a little bit of description of the Carnot engine as well. So later on we will see how this ties in with the second law of thermodynamics also. 10.2.7 is simply solving problems using the first law of thermodynamics and the work equals pressure times change in volume. So yeah, that should cover 10.2. Now we'll move on to the second law of thermodynamics and entropy. Okay, 10.3 is the second law of thermodynamics and entropy. So most of the students may not have come across this term entropy before. It is a measure of the disorder of a system. Okay, so the more disordered a system is, the more chaotic a system is, the higher the entropy. Again, just like internal energy and heat supplied, you cannot actually measure the absolute entropy. However, you can measure a change in entropy, and a change in entropy is denoted by delta S. Okay. Now, the way to calculate this change in entropy is the amount of heat, okay, either taken away or supplied, okay, to or from a reservoir divided by the temperature of that reservoir. So, for example, over here you can see the change in entropy delta S of a system when an amount of thermal energy Q is added to a system by a reversible process at a constant temperature T. Okay, and from here you can know that the units are joules per Kelvin. Okay, so in IB it's sufficient to know that it's the change in heat divided by the constant temperature. Now you should know that this is a reversible process. It should be a reversible process, but in IB it's sufficient to just know this. Okay. Now, the second law of thermodynamics has to do with entropy. Now, let's say we have an engine. Okay, and the engine is operating in between two reservoirs, a hot reservoir at temperature TH. QH is the energy taken away from the from the hot reservoir. QL is the energy which is supplied back to a cold reservoir. Okay, at TL. Now, the first formulation or the first form of the second law of thermodynamics says that no heat engine operating in a cycle can take in heat from its surroundings and totally convert it to work, which means that QL equals 0. Let's see how that ties in with entropy. Again, before we go there, the first and foremost definition or the first and foremost formulation or the major formulation of the second law of thermodynamics is that the entropy of the universe always increases or can never decrease. Okay? This means that the change in entropy of the universe is always greater than or equal to 0. Now, change in entropy of the universe, in this case, this would mean the change in entropy of our system. In this case, the engine would be the system, added to the change in entropy of the surroundings should be greater than or equal to 0. Right? Now, let's see how this ties in with this definition of the second law. Over here in the hot reservoir, the change in entropy of the hot reservoir would be minus QH, because QH was the heat taken away, divided by TH, and over here the change in entropy SL, delta SL will be plus QL over TL. Okay. So the change in entropy in this case, since we are assuming no heat loss of the universe, will be equal to delta SH plus delta SL, which is equal to QL over TL minus QH over TH. Okay, so if QL is 0, we know that this entire quantity will be less than 0, since TL and TH are both positive, and QH will be positive as well, so minus QH will be negative. So therefore that is not possible, because it would violate the second law of thermodynamics, which states that the entropy of the universe can never decrease. But the second formulation is also related to this, which states that no heat pump can transfer thermal energy from a low temperature reservoir to a high temperature reservoir without work being done on it. So again, it's pretty straightforward. If you work this out for a heat pump, you should also be able to work it out using entropy. Now, another meaning of this is how this ties into Carnot. The Carnot efficiency is that, remember, for an engine, if the engine obeys the second law, it must have efficiency less than Carnot engine. Carnot efficiency, which means that the efficiency must be less than 1 minus TL over TH. Okay? This can also be proven using the same method that I just used, but it's important for the students to remember that this is how the second law ties in with the Carnot efficiency. The moment an engine is exceeding its Carnot efficiency limit, that means it is not obeying the second law of thermodynamics. In the last part over here, there is a discussion of example of natural processes in terms of entropy changes. For example, when there's the formulation of an egg. So within the egg, the entropy goes on decreasing because the amount of order is increasing. That means the disorder is decreasing. Entropy is disorder. So why is that? How is that possible when we say that the entropy of the universe increases? So therefore, since the entropy of the system is decreasing, we know that the entropy of the surroundings must increase by a greater amount. Okay? So therefore, when the egg is being formed, there is thermal energy released, and released so much so that the surrounding area has a greater entropy increase than the decrease in entropy within the egg. So that's a descriptive process which the students might have to describe in some parts, some later parts of the questions related to thermodynamics. So there are a couple of examples here in 10.3.4 which have natural processes in terms of entropy changes. So yep, that's pretty much thermodynamics, and now we'll move on to the next chapter.